Greetings, everyone. This is Eric Andelin with SimActive. I am your senior workflow specialist, and today you're joining us for a webinar on choosing the right camera for your mapping project. And I have with me my guest speaker, Pat McConnell, president of ClearSkies Geomatics. Pat, say hi.
Eric, nice to see you.
There we go. Now we're off. We're off and running. So there's a few things. My background in photogrammetry is well known. You guys are familiar with that. There's actually some pictures back there of me doing survey and stuff. But Pat, tell us a little bit about yourself and what you guys do.
So, ClearSkies Geomatics is a company that buys, sells, and brokers aerial survey equipment around the world. And how we do that is through this web portal called aerialsurvey.com. And so we have several. We have a business in the U.S. and we have one in Ireland, and that those businesses do essentially the same thing, but under the aerialsurvey.com umbrella. So we move lidars, all forms of cameras, airplanes with holes in them. We like the ones with holes.
Yep.
And we sometimes provide consulting services, and we also do estimates, I guess, valuations, equipment valuations for banks.
And then I would think to some degree you're helping your customers kind of figure out what equipment is right for the type of work they're doing, and maybe all the ancillary products that they would need to be successful in that business.
Right. We often get calls from clients who, ask for our advice to figure out what's the best solution, the most cost-effective solution for their particular needs. And we've become a trusted advisor out there because we're not married to any of these manufacturers, so we can provide unbiased opinions and provide people with what we think, and it's usually free. So it doesn't hurt my feeling if they don't take our advice.
Sure.
But the advice is there. And I've got 20 years of experience just in the airborne business. So
right.
It's useful information.
Yep. I know we go way back.
Yes.
So to do just a little bit of housekeeping, for the folks that are joining us on the webinar, we will see your questions. I am bouncing back and forth between a few programs here as we do this. So if I do not answer your question during the webinar, I'll make sure that it is answered after the webinar. I just put up a graphic. So we're going to talk right now a little bit about what you're going to learn in this webinar. We're going to talk about types of cameras used in aerial mapping. We're going to talk about single sensors versus multiple sensors. We'll talk about the additional components required as part of this system, factors that affect accuracy, and then in the end, I'll jump into a little bit of a demo or some samples from projects we've done in correlated 3D so you can kind of see the differences.
I'm liking it.
Good, you're part of it. So let's talk a little bit. We're going to talk a little bit about types of cameras. And again, I've got a graphic up, and we're talking about maybe a little bit of a timeline of cameras. And we start back in the 20s with handheld aerial photography and aircraft. A gentleman named Fairchild started kind of this process with aerial mapping. At one point, he had 90% of all aerial mapping cameras for the military, aerial photography cameras.
Right.
And then he went on to develop some of these technologies that are still here and that will move forward. Actually, he sold his company to IBM at some point. But in the 20s, that was kind of handheld, hold it over the side of the plane, the biplane or whatever, and take your photos. And then we moved to cameras with, aircraft with holes in the bellies and cameras in the bottom. They may have intervalometers in them, which helps the pilot track when the next photo is going to get covered, collect stereo images. And then the next advances we start to see are, cameras like the RMK. They start to use mounts to kind of even things up. After that, that was say in the 60s. In the 80s, we start talking about cameras like the RC30 that is made by Leica and comes with a gyro stabilized mount. Then we move on to the digital cameras in the 2000s, and they just take off. There still are film cameras in use, but the majority are digital cameras. And with digital cameras, we see the combination of multiple sensors. So, maybe the footprint at the time from that digital camera wasn't big enough to cover the same format as a film camera, so they started using multiple sensors. And then finally, where we're at now is we're starting to look at more camera options, medium format options, even the options to use commercial off-the-shelf cameras like, say, a Sony a6000 or the little camera that's in your DJI Phantom 3. Those are, a whole different breed, but we can use those. I'm not saying you go back to the 20s, because you don't, because we're about the same age. But
thanks a lot, Eric.
Yeah, you're welcome. Given that, we're probably both got involved in the 80s. Myself, I was thrown in the backseat of my dad's plane because I did something wrong at school in my junior year, and that was my penance for my summers. That's how I became a aerial cameraman. And that family business still exists. I don't know if we continue to punish our family members by putting them back there, but it's there. So you fill me a little bit in on where you slid into the technology and how things move forward.
So I became involved in the camera business in 2007. And 2007. It was interesting times because it truly was in this transition of going from analog cameras, so the RC30s and the RMK camera series, to digital cameras. And Zeiss had the DMC1, Vexcel had the Ultracam D, then the Ultracam X. And so truly at the infancy of these kind of large, what they called at the time, large format digital cameras, and kind of the tail end or the beginning of the tail end of, the analog world. So it was interesting times because we spent a lot of time educating our customer base on the differences between it. Digital world lives with GSD, where the analog world lives in photoscale. And just that understanding that transition and learning about it and what does it mean and how do I explain this to my customer. So a lot of the effort was put into educating people about those differences. And then we also, I think back in the day, the pitch was, well, you're going to save a lot of money. And I think to a certain degree that was true because you certainly didn't have to worry about wasting film if your exposures weren't right or, you were, for whatever reason anyway. It's digital is great because you're basically storing data onto cheap hard disks.
Yeah.
Like cheap cost-wise. And so from that perspective, I think it was correct to say that that there were some cost savings to be had. Now, the other side of that coin, though, is because the actual area that you were capturing was smaller with the digital camera, I think it was probably 30% or maybe 40% of the size of a say 9x9.
Yeah.
And so there was more cost to actual acquisition, but there was also maintaining these digital cameras. And so we're talking about computer parts and, computer boards and all of that stuff and getting on maintenance agreements and, all of those things brought along a cost that, makes sense today, but maybe back then when you're comparing, well, what are the costs of processing a film and scanning it and storing it and so forth. So, I think that one of the mistakes I made when I was trying to sell digital cameras at the beginning was just trying to really pitch these cost savings. And I think at the end of the day, there were some, but I don't think that I was really um, recognizing the additional costs that weren't being counted when you're trying to sell a digital camera. So, but today, what are we looking at today? We're looking at 99.9% of the market has gone digital, and you still got a 0.01% of companies out there, like your family's company, who still fly analog cameras and still deliver products that the customer demands. It's
until the film runs out. They're in use,
exactly.
And it's not necessarily my family that's they're not the only ones flying them. They fly other cameras as well, but it's the end user. It's whoever the mapping company is. They may still be using old analog stereo plotters, and they find it efficient, and that's the way they want to do it.
Getting somebody to try something new is really tough in our industry.
Yeah,
so I think
life was a lot simpler when you had the old aerial mapping cameras. You had two lens configurations, either a 6-inch or a 9-inch lens. It was almost always a 6-inch lens. You had your film, which was 9-inch. So it didn't matter what stereo plotter you were working with; they were designed to handle that. And like you said, the mechanics or the mathematics of photogrammetry is pretty straightforward. And to set up stereo models and to be able to view those, it's pretty nice. And not only that, but like you said, photo scale versus GSD or map scale versus GSD. When you had, when you were flying for a map scale, there were set altitudes. If you want 1 foot contours, you're doing this. You want 2 foot contours, you're doing this. When we bring GSD into play, and now different cameras configurations, that changes based on the camera that you own. We're talking now about additional components, such as a gyro stabilized mount.
Right. So I think gyro stabilized mounts are really a big advance. And the whole purpose, it serves three purposes. So number one, it eliminates most, if not all, of the vibration that you would feel on a propeller-driven platform. So whether it's a single or a twin, those propellers create vibrations to the aircraft, and the sensitive equipment, cameras and lidars, all could react to these vibrations and create problems when you do data acquisition. So there's these passive vibration rings that basically go inside of the mount that help stabilize your sensor from all of this vibration that's happening around it. Right. The second thing it does was, and one of the reasons why these mounts were created, was to manage drift. So, you could be flying a straight line, a side wind comes in and knocks your tail sideways, and all of a sudden you're flying in a straight line, but your plane is skewed, right? And so the mount will automatically correct for that skew and put it directly in line with your flight line the way it should be. Mm-hmm. So you used to be able to do that manually, but now it's all automatic, and it's tied into your flight management system and GPS and all that good stuff. And then so that's really great, because then you have less of this crab correction that you need to make when you've downloaded your data. And the final thing is the ability to manage in near real time the plane movement. So whether it's a yaw problem or a roll problem, the mount has a fairly large degree of flexibility to correct for those movements in pretty close to real time. So the product that you get out of your sensor is pretty rock solid.
I've actually got a graphic up here now, and it actually shows the gyro stabilized mount in the RC30. It also shows a flight management system, which we haven't talked about that yet. When your buyer comes in and they start looking at specific sensors, flight management systems to do the mission planning, in some cases tell the camera when to fire.
Absolutely. The technology that's involved in these flight management systems are so automated now. It knows when to turn on the sensor. It knows when to turn it off. It knows how to deal with, switching lines from one to another. It knows how to reboot itself or not trip into, service mode where it's like, oh, it's too much tilt here. I can't handle this. So the flight management systems today are pretty sophisticated.
And then in another photo there, we have a picture of a laser scanner on a tripod, and it's actually scanning the GPS antenna and the camera, the center of the camera, or the offsets, so that when that's all put together with an IMU, you're getting proper image positions in your EXIF data or the file that you use as EXIF data. You don't necessarily need all of that to do photogrammetry. You can always solve using the principles of photogrammetry, but those things help as far as the airborne GPS and the IMU, because when we bring it into our software, we can use that to interpret more easily where those image positions are. Again, without them we can do it, but if they're there, it's nice to have. It's an extra expense. It's a big expense, but it may be worth it.
Well, especially if you've got a software platform that it can accept maybe a smaller version of big data, right? So the more information you can give your software to be able to process these data sets, the better it is.
And then the last photo for everybody, the last one on the right, is actually my favorite living brother. His name is Don. I know him as Jim. And on the co-pilot seat is my nephew, Tony. And they're still out in Southern California flying. And as you can see, they've got an Ultracam. I think it was an Eagle, but they've got that in there. But the fact that they're both sitting up in the front seat, and Tony is just managing that sensor. All he's doing is making sure it's working. It's taking the photos as it goes. As opposed to, when I was relinquished into that job, I had to sit on a 5-gallon bucket upside down with my head down there, looking through that viewfinder and taking the photos. So I would say life has gotten a little bit better. Technology has certainly helped, these two out be successful in their business.
Right. So I guess you were the flight management system at some point.
I was the flight management system for a little while. So
I think it's terrific, and it's nice to see the software kind of advance at the same rate. Speed of processing, for instance, I think used to be a big deal. I mean, these images are not small.
Yeah.
And the fact that your software actually runs on a PC using inexpensive video cards to help speed up the process, I think is a really, really good thing.
Absolutely. I saw something the other day, somebody posted on LinkedIn, and when I was reading it, and said, "When's the last time you used a scale?" And I was like, the last time I used a scale was to lay out photos. And that's been a while. So I don't miss those days. So another thing before we move on, so we've talked about camera types. We've talked about single sensor versus multi-sensor. We've mentioned the other ancillary items that you need as part of this package. And now, one other thing I'd like to at least touch on is these integrated systems, where we're talking now about LiDAR and imagery. So what are your thoughts on those?
Well, when the conditions are perfect, I think it's a great solution. But as you know, rarely are the conditions perfect for acquisition. The cameras won't work at nighttime, but nighttime's a great time to fly LiDAR.
Yeah.
Right? And so that's a little bit of a challenge. The actual camera, one of the nice things about, when everything works, it's fantastic because all of this equipment fits on a mounting platform that fits in a standard camera hatch, which is really, really nice. So if you've got perfect conditions where the sun is shining and you've got great sunshine on your targets, having a camera working at the same time as your LiDAR is fantastic. But hopefully your client is happy with the resolution, right, of the imagery that you're collecting while you're collecting the point density that they want. So that's that could be a challenge as well. I mean, maybe they want higher resolution, And so I think in principle, it's really cool that you could do that. I mean, the miniaturization process of computers and computer components has made it possible to actually put this all together. But we're still struggling with being able to make full use of it, because at the end of the day, customer requirements might not be right for making these dual acquisitions in one pass.
Right. The challenge is always what is dictating the deliverable. Is it the point
Right.
density? And if it's the point density, then the altitude you're flying may not match the coverage of the sensor for the camera.
Right.
So you have that challenge. And like you said, you have flying LiDAR is best at night if you can.
Right.
So you have that challenge. At least like you said, we're down into the miniaturization part where you can fit it all in a camera barrel.
Right.
So you only need one hole in the aircraft.
Right.
When they were trying this originally, they were poking two holes in the aircraft. They had two big sensors in there, and good luck if you had enough power to fly the plane and run the equipment. So we've gotten past that, so that's great. We've even gotten to pod systems that you can put on the belly of a helicopter or slide out onto the strut of a wing, which brings into focus the medium format cameras. Right now, one of the really hot cameras out there right now are the phase ones.
150 megapixels in a little, you can hold it in one hand, is pretty impressive. When 10 years ago, 150 megapixel camera weighed a couple hundred pounds.
Yeah.
It took two people to install it in a plane. So that's a good example of how miniaturization has really changed how we can do our business. And so the cost has gone down, hundreds of thousands of dollars compared to $1 million or plus. And also to manage, these amounts necessary are to drive these things are a lot smaller, a lot less expensive. They use the same IMUs, same flight management systems. So some of the stuff is still the same across the board. But at the end of the day, I guess the question is whether or not the client wants this data. And I still see, to be honest, in the market some resistance of using, kind of what they call a medium format camera as a deliverable to some clients. It's not clear to me why. I think the radiometry and the geometric accuracy ought to meet the deliverables, but for some reason, some people still like to use just the kind of what they call engineering grade or metric grade, like truly metric grade camera systems, like Zeiss or Leica now, and Vexcel's cameras, the Ultracams.
Yeah.
So well, it's interesting that you still see that division.
Yeah. To me, we can go into this now when we talk about factors that affect accuracy, because now we do see off-the-shelf cameras being used as well. So we see Sony A7s, Sony A6000s, whatever the drone manufacturers' cameras are, being used for mapping, which they can. Fortunately, we have the software. There's other software out there that can solve for any problems there. But prior to that, as you mentioned, we're talking about metric cameras, and metric cameras were designed to withstand the effects of atmosphere in any way. So, the body of the camera, the lens itself, no change in air pressure or temperature or humidity would affect the geometry of those. Therefore, it was rock solid, and you didn't have to worry about it. And those cameras came, as well, usually with a calibration report, which we'll talk about calibration reports, because it's nice to have, but it's not necessary, or not always necessary.
Right.
And historically, when we go back to the film cameras, we had a regional authority who said, for your camera to be used for this purpose, you have to send it in and get it calibrated every 3 years, and it has to meet a certain specification. And we're going to give you all the parameters from that camera that you can then use in your photogrammetry software and produce quality results in your AT. Those days are gone for the most part. Now we have either a manufacturer's calibration since we went digital. And honestly, those government labs couldn't handle it.
Right.
Um,
Right.
because they wanted it a specific way. And now we've got, like you said, digital cameras where we're talking about GSD and things like that are.
I personally don't have a problem with manufacturers providing calibration reports, especially with I think it should be an automatic deliverable. It's nice to have, I think, a kind of a baseline.
Yeah, it's like a spec
Right?
sheet. Almost.
It's like a spec sheet, but I mean, you got to start somewhere.
Yeah.
And certainly, you'd like to see if there's change over time.
Mm-hmm.
It would help the manufacturer, I think, maybe understand what's going on. But I guess one of my it's not a pet peeve, but I mean, I actually prefer field calibrations over lab calibrations.
Mm-hmm.
Because I think it's especially if you're doing it on a project basis. So that day at that temperature at that elevation, this is the calibration I'm getting out of my system.
Yeah.
And to me, that's more relevant than something that was done in a very clean environment, because we don't work in a clean environment. We're dealing with fast temperature changes and atmospheric effects out there, haze or whatever. Mm-hmm. And I mean, your lens shouldn't be distorting if it's a decent system, but I don't know. It's just, I think it's a little bit like Mac versus PC, where people believe more in the lab calibrations as opposed to the field. But I'm a big fan of field calibrations.
Yeah, and our users know this, but when you're working with a camera, and I'm not picking on anybody, but I'll use Phase One for example because I really like those cameras. They provide a calibration report. You can import that calibration information into Correlator 3D. I will harp on Regal a little bit. They should do a better job of how they represent the calibration report.
Easy.
They do it for another software, and we have to reverse some things. Just make it in the right format. Right. But in either case, because I mean they're a system integrator, what's most important to them is their LiDAR system. But when you bring that information into our software, anybody's software, you can bring it in and hold those constraints. So you could say, there's two things you could do. You could say, I am absolutely confident in what the IMU is telling me, and therefore the XYZ omega kappa phi, don't touch it. And then you would run the AT that way. You could also then go and say, well, I have a calibration report on this camera. I'm going to input that calibration information, and then I'm going to tell the software to constrain the camera to that as well. And when you do that, your results are probably going to be good. They may be a little off. It's up to you to decide when you're measuring against control. But one way you can always check it is to unconstrain those things, and then let the software process it. And it basically does, a backwards calculation and figures all those things out. And it will give you a new calibration report, and you can compare the numbers. And if the numbers are pretty darn close, you're probably in good shape. Probably everything's okay. It's up to you which calibration you want to use, the one that the software created or the one that, came with the camera. And, over time that may change. But in the software, you can then save that new calibration and reuse that for a period of time. When you're working with a metric camera, you can reuse that a long time. When you're working with, off-the-shelf Sony A6000, every time you land hard, you probably should do another calibration. And like you said, field calibration really is something like if you're flying out of the same airport all the time, that's your base, have a field set up where you've got a series of targets built out there. So that you've got something to compare to as maybe you're flying out to your project or maybe as you're flying back. Just grab that area and then you can compare it over a series of time and
Right.
see how everything's working. With a metric camera, you should be able it should be reliable over a period of time. With an off-the-shelf camera, I'd almost recommend just make sure you have a lot of control and let the software take care of it.
So I got a question for you, Eric.
Uh-huh.
So we've talked about all these, these different cameras. We got, the large format, medium format, and commercial handheld cameras.
Mm-hmm.
And maybe I would say maybe 10 years ago, you'd never consider a handheld as a piece of equipment that would generate accurate mapping products. So what do you see kind of in general with accurate, all these different levels of camera, now that you've got powerful software, right, that can calibrate on a project basis?
Mm-hmm.
How do you see the differences in accuracy in the final product now? Is there a big difference or is there no difference?
Well, it's almost a little cloudy because when you see the off-the-shelf cameras, they're typically attached to drones, which are flying at low altitude and capturing tons and tons of overlap. So the inherent distance from the ground is going to make it easier in some instances to be more accurate on that control. But it also creates problems because being that low, you've got more change in the radiometry of the lens versus the ground. So, the software has to make up for that. And in all reality, almost nobody's doing stereo imagery from drone images because the footprint's too small. To transition from one model to the next is a real pain. Therefore, you tend to see with the off-the-shelf cameras, you tend to see a little bit more parallax when you're actually setting up stereo models. But who does that? But you do see it. The software mitigates some of that. It's like the discussion of a mechanical shutter versus a rolling shutter. Software can mitigate a lot of the issue there. And although in the drone world, we would love to run around and talk about how we can do 6/100ths of a foot mapping and create contours at a 1/4 foot, that's nonsense. Who really wants that? Your mapping companies still do mapping based on 1 or 2 foot contours or something like that. And those projects are typically flown with larger format cameras or medium format cameras at higher altitudes with metric cameras that tend to do a little bit better. So,
but from an accuracy perspective, though, are you seeing a difference in map accuracy between, so if you're to snapshot today, with what we've got today, we got large, medium, and commercial off the shelf. If you were to compare the accuracy, the mapping accuracy of those 3 cameras, because now today we didn't have powerful software 15, 20 years ago. I mean, we had stuff that was doing a job, but it's certainly not the way it's doing the job today. So I'm just wondering how big an effect does software have on accuracy, given the hardware differences in of its own? The stability of a commercial off-the-shelf handheld camera is not the same as the stability of a large format camera. Like, they're not made from the same material.
Yeah, but to me, it's kind of like going from an LP to a CD. You lost a lot of fidelity, but does anybody care? For convenience, they don't. And honestly, again, the off-the-shelf cameras are doing stuff that's modeling, some mapping, things like that, but they're not really, they haven't taken over the market. They haven't taken away even a reasonable chunk of the market of mapping. So therefore, I just don't know if we see it that much. The medium formats are to me are just as good as the large formats. They're
From an accuracy
certainly,
perspective.
yeah, they're
Right.
certainly allowing people to enter the market that on an investment wise that might be a little bit easier to swallow than a large format camera. um,
Right.
uh, and then you go back to the argument of single sensor versus multiple sensor, which direction those sensors are facing, how nadir they are, how oblique they are, how's the software stitching all that together. That might cause issues in the large format world, but I doubt it. I mean, more,
That
from,
problem, that problem was solved years
yeah,
ago.
yeah.
I can't remember seeing image formation off of a DMC or an Ultracam that had stitching issues.
Yeah. Yeah, and to be honest, from my own perspective, I have never looked at a DMC image in stereo or anything like that. So I
Right.
rely on you for that because I have not done that. But I would say that, again, given what you're using a off the shelf camera for, I don't know that it's really that.
Not that relevant.
Yeah, not that relevant. Um,
Okay.
yeah, I mean that's really all I could say to that. But a couple other things we can talk about, which affects all of them. Altitude. We talked about that just a minute ago. A proximity to ground. When you're flying something with a drone and you're 300 feet off the ground and the trees are 100 feet off the ground, as you stitch all those together, you get all kinds of lean. But with large format, now we're talking about things like altitude and speed. So what is the speed of the plane do as it's going across the surface?
Mhm.
How do we mitigate for that? What is being done to mitigate for things like that? So image motion and things like that.
Right. Well, image motion is a really interesting technology or problem because there's a lot of different ways to try to solve it. Right. Um, you've got in the CCD world, they used this thing called TDI, time delayed integration, I think.
Uh-huh.
And so it would basically manage the pixels on the CCD when they would turn on to actually acquire imagery. And that would certainly, up to 50 pixels, I believe, manage motion compensation in the direction of flight. Now all the camera makers are moving to CMOS, and you can't do TDI anymore.
Mm-hmm.
And so how they solve that problem are three other ways. They can have a super fast shutter speed, and phase one have adopted that technology.
Yep.
So basically, the thinking there is, well, your plane's going to fly at a certain speed, but if I'm taking an image at 125 hundredths of a second, then you're not going to see any blur. And I think most of the time they're right, but it certainly doesn't solve it 100% of the time. You'll get some image blur some of the time, depending on your aperture, lighting conditions, like wind conditions, even in an airplane,
Sure.
right?
Yeah, it's not just blowing. It's not just going straight forward. It's sliding back.
It's all over the place, exactly.
Yeah.
And then you have the mechanical forward motion compensation. So it's basically a device managing your CCD inside of the camera head. So that also works pretty well most of the time, but it's something that can fail because it's a machine. It's something that moves. And then finally, the newest stuff that's out there, I think it was developed by Vexcel, is basically all the motion is compensated through software, and they've figured out a way to basically eliminate motion in any direction, and that's pretty amazing. I don't know that anybody else does that right now, but certainly as Vexcel moves forward with their new systems, which are driven with CMOS chips as opposed to CCDs, that's a pretty impressive change in our market. So I'm looking forward to seeing the results of that. But there's a lot of solutions to fix that one problem.
One of the last things I wanted to talk about, it's just in real briefly, I'm going to go ahead and get into the demos here in a bit, or some
Right.
examples. But Correlator 3D doesn't really care what camera or what sensors coming into play here. we work with UAVs, which we consider under 50 megapixel. We work with medium format, which is up to 100, large format, which is above 100 megapixel. Then we also work with some of the older technology. Of course, we can use film cameras. We can, if it's a scanned image, we can import that and work with it. There were the ADS broom sensors.
There's still some there's applications like NAPE, for instance, is a project that still like to use the line scanners. So there's certainly some applications that are well tuned for line scanners.
And then one of the original city modeling tools out there, an A3 camera, which I believe was developed by an Israeli company.
Vision Map. So it's basically two 25 megapixel cones, but it would basically rock back and forth like this. So you have two cones, one beside the other, and they would rock. So each image was 25 megapixels, but the swath was huge, crazy big. It was, I think it was like 80,000 pixels wide was a swath.
Yeah.
And so it would just collect these 25 megapixels really quick, click, 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 swing back, click, 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 click. And it was a pretty amazing technology.
Last thing, I know that, and I'll extend the thanks. I know that when Philippe and I talk about you, Philippe's the owner of the company here at SimActive. He always credits you for being involved in bringing SimActive into the States. So I'm passing along the thanks.
Well, we tried. It was early days for both of us. So we sold a few copies, but we certainly talked about the product a lot. And I'm really happy to see the kind of the growth of the product and the business over time. It's really nice. And I hear now that SimActive is starting to dive a little bit into the LiDAR processing side. So
yeah, well, I think because we have these integrated systems, you can bring process LiDAR data in, which then allows you to skip that step in building a digital surface model. So maybe, if DSM creation is 20% of the processing time and you've already got a LiDAR point cloud, bring that in and use it as the surface.
Nice.
And out of love for you who bring in LiDAR point clouds, we can then take that mosaic that was created at the end and colorize your point cloud. So now you've got, an even nicer product to deliver to your customer.
Nice.
So
nice.
So yeah, we have added it in as our users ask for certain things,
sure,
if it meets the required criteria, we're gonna add it in. Okay, Pat, sit back and relax, and let's get into the demo for a bit.
Sure.
Bear with me as I get Correlator 3D up and running. Okay, let's look at a few things. In the essence of time, the processing is pretty much the same. What we're looking at is how we set up a project. So we will go ahead and create a project here, and bear with me as I do this. New project. We're using, in this case, we're going to use phase 1 imagery as the example. We'll find the folder with the images, which I believe is this one here, all IIQ. And it's asking for the CSV that goes with the images. I believe it'll be this one here. Okay, so now we have our EXIF information and we can import the imagery. We can uncheck this one. Change the file name. Oops. Easting, northing. elevation, we can let all those slide. And the projection. North. There we go. So the images are all ready to go. And here is where we are going to bring in the camera calibration information. So again, Correlator 3D will analyze the images and figure out a few of the items that we need. So for example here, image height, image width, focal length, and pixel size. So we have all those in there, and we can work with just that. So the software will do its own calibration using those values as the base. However, in this case, we do have a calibration report. So let's take a quick look at the calibration report. Let me find that. Should be here. This calibration report. Because this sensor, this phase 1, was used in combination with a Regal sensor, Regal went ahead and did the calibration for the camera. And you'll notice a few things that present, again, not a big deal, just the way that Regal produces its calibration report. The sign of all parameters must be inverted. So when you import these in, we've got K1, K2, K3, P1, and P2. Those would need to be inverted when we put them in here. Not hard to do. Just as you're manually keying these in, you're going to want to make sure that you change these values. So for example, the first one would be, let me get back here to the report. Let me just grab it. I'll just take it from here, copy. K1 is going to be, I'm just going to go ahead and make that a capital E. And it's going to be a negative value. K2, we go here, same thing. This is going to become a positive value. Control V. That's going to become a positive value. I'll go ahead and just make this doesn't really matter there, but habit. And you would go through and fill these out for each parameter available. As you can see, they're here again. You could take that information. Now note this calibration report from Regal is fairly large. It also has, a distortion table. It also has a little bit more information on, positioning or offsets related to both the LiDAR unit and the camera. And then there's another camera calibration report down here. Don't make the mistake of using that one. That's not what we want. And then there's just some additional Regal information. Now, just to show you a little bit of a different calibration report, this also is a phase 1 calibration report for a different camera, but this one comes directly from phase 1. So as we look at that one, it's giving us general information on the camera, and what we're looking for here, here is a calibration result in Australis format. We don't work with that one. They do provide the calibration report in USGS format, which is kind of more standard here in the States, is what we would use. So same thing, we would input those parameters in here for that camera, and we could work with that. Now, just so you're aware, once we start the project, and I'll just go ahead and next, I'm gonna cancel out of this. What we could do is we could import those camera values. So for example, if I wanted to import those values and they were in a file, I could do that. Let's see. Find here, camera related files. I had created one earlier called SimCal. So as you can see, I just grabbed that file and it went ahead and loaded all the information in for us. And that's just through the import process. So if I hit next, give it a project folder. select that, hit finish. Now it's gone ahead and it's loaded all our images, and we would begin, our standard processing methods. So let me hop on over to a finished project here, and we'll go File. Let me switch to this project, and we'll let it load. And if we look at the AT, turn off the references. If we go to the AT, we can look at the bundle adjustment steps that were performed. So if we look at, for example, step 3 is the most recent, we can see that in this case, we fix the sensor calibration is fixed, which means we're using the calibration report and we're not adjusting the image parameters. Same thing with the EO adjustment. So we're using the IMU information from the aircraft. And we can see that, again, image adjustments, none. Sensor calibration, none. So it's pulling all the information as is. And then just a little bit of information on the processing software. And how we did that was in the bundle adjustment, we went full AT constrained, and we sent the camera to constrained. So that's how you would do this if you wanted to use the calibration parameters provided in the calibration report. Now, that's great. You can use it. But again, we talk about, there are occasions where, especially in the world of off-the-shelf cameras, or maybe cameras that have not been calibrated in a while, if you start to notice your accuracy slip, what you want to do then is do a calibration where you unconstrain the camera, which then lets Correlator 3D do the calibration or create a calibration itself, which it does, and it works perfectly fine. So I'll go ahead and cancel out of that. And the last thing I want to show you is, again, how we make that calibration report. So once we're happy with what we've got here in the AT, we can go ahead and get out. We can go ahead and get out of AT. Once we're happy here in our results from the AT, all we need to do to save that calibration report is come down here to Export, and it says EO and calibration, or EO and camera. We just hit text file and then give it a location. So let's say, we just say new folder. We'll say cal report. Put it in there. And it's gone ahead and exported that calibration. So we can go to the folder. Let's see here. Sorry. Go to the folder. And we'll go here. Calibration. And now we have a new calibration file. If we open this up, it'll look familiar to you here. We have a calibration file. Once we have that, again, now we can save this out. So we can save it out and we can reuse it and just import it in the next time we start a project. So that's very helpful. It also does provide the EO information, and the EO information is basically the adjusted positions of the images that you could, say, bring into another software if you were doing stereophotogrammetry or something like that. So that is there as well. From there, the processing steps are the same, so we don't really need to cover that, but be aware that they're there. It doesn't matter, again, what type of camera you import. A calibration report is great to have to start with as your base. And then, as I said, the minimum things you need and the things that the software will pick up on its own are image height, image width. It'll pick up focal length, and it'll pick up pixel size. And if you have all of those, you don't necessarily need a calibration report from the manufacturer. Our software will create one for you. Again, the other step is that if you do have a calibration report, you can import that calibration report and use that as your base. Process it that way. If it looks good, stay with it. If the numbers look off a little bit, then go ahead and unconstrain the camera and let our software do the calibration, and it'll show you a comparison of in the results of the two. So you always have that option. So I know we went long in this demo, and I'd like to thank you for staying with us. I've seen some questions, and we'll get those questions answered for you. I'd like to thank Pat for joining us. Any last words?
You're welcome.
Perfect. Perfect. Good last words. And I wanted everybody to know that at some point, this webinar will also be turned into a podcast. You can find that podcast on all of your favorite podcast sites. It's called Pixels and Points. And again, thank you, Pat. Appreciate it.
Thanks for having me on, Eric. Take care.